This video lecture is meant to cover the information from Unit 13 from the gas laws, objective number 4, where we will describe how pressure, temperature, and volume of a gas vary if one quantity is changed. We've already seen in class our little PTV strip, which helped us remember how these variables would change so long as one variable remains constant. We have seen that if you increase the pressure while keeping the temperature constant, if you increase the pressure while keeping the temperature constant, the volume will decrease. If you keep pressure constant, so pressure is going to remain constant. If you increase temperature, right? So if you hold pressure constant and you raise the temperature, the volume will also increase. If we were to keep the volume constant, we start this over again, and you were to increase the pressure, the temperature would also increase. So these were the three scenarios that we saw when you have pressure and volume changing and temperature remaining constant. This was referred to as Boyle's law. When pressure is constant and just temperature and volume are changing, this is what we call Charles's law. And if volume is constant and just pressure and temperature is changing, this is what is referred to as Gay-Lussac's law. And what's not as important as knowing the names is knowing what happens when you manipulate the variables. And of course, why it happens, and this all relates back to the kinetic theory of gases. All right, so let's take a look at some specific examples here. We have a gas at a constant volume. All right, so there's some clue words right there. There's a constant volume. Initially, the gas is at a pressure of 1 atmosphere and a temperature of 200 Kelvin. So we have 1 atmosphere being our pressure, and our temperature is 200 Kelvin. And we're going to approach these problems today without a calculator because I really want you to understand mentally what's going on without being dependent on calculator work. All right, so if we have a pressure starting at 1 atmosphere, and in scenario 1 right here, what would the temperature be if the pressure is increased to 3 atmospheres? So if the pressure starts at 1 atmosphere and increases to 3 atmospheres, right, that's an increase of a pressure by a factor of 3. So knowing that volume is constant, right, we should now recognize that what will happen to the temperature is that the temperature should also increase. Right? So it'll increase by the same factor. So since the pressure increased by 3, the temperature should increase by 3. Well, since the temperature started at 200 Kelvin, if we were to increase that by a factor of 3, the final temperature would end up being 600 Kelvin. So that ends up being our answer for that first scenario. This only works if the temperatures are in Kelvin, so if you are given a problem in Celsius, you would have to at least first change your temperatures to Celsius. Okay, so take a look at scenario number 2. Scenario number 2, starting with the same initial conditions of 1 atmosphere and 200 Kelvin. Consider for a moment what would the pressure be if the temperature is decreased to 100 K, so from 200 K down to 100 K. Ask yourself what's happening to the temperature. That's right, temperature is decreasing by a factor of 2. It's decreasing by half, okay? So that's by a factor of 2. So we know that the pressure will do the same thing as the temperature. If the temperature is decreasing, the pressure will decrease also by the same factor, okay? So if the pressure was originally at 1 atmosphere, it's going to decrease by a factor of 1/2. So from 1 atmosphere multiplied by a factor of 1/2, this new pressure would end up being, oh, I wrote my decimal wrong, 0.5 atmospheres. All right, let's take a look at the second problem here. Again, no calculators. We are starting with a gas at a constant temperature. Okay, so what we're going to see here is pressure and volume changing. Remember, pressure and volume are an inverse relationship. As one goes up, the other goes down. Our initial conditions are that the gas is at a pressure of 1 atmosphere and the volume is at 3 liters. What would the volume be if the pressure was decreased to half of an atmosphere? So pressure is decreased to half an atmosphere. So from 1 atmosphere down half an atmosphere, that's a decrease in the pressure by a factor of 1/2. Okay? And so we know that the volume is going to, since it's an inverse relationship, the volume is going to increase by a factor of 2. Okay? So this is where you have to be careful. If you're dividing by 2 for pressure, you would have to then multiply by 2 for volume. So the volume in this case would go from 3 liters up to 6 liters. All right, I'm going to let you work through scenario number 2. I'm not going to give you the answer for this. You're going to bring me the answer tomorrow. So pause the video right here, take a moment to work out the problem, circle your answer, and bring it back to me in class tomorrow or the next time that we meet. Let's take a look here at our next problem. Here we have gas at a constant pressure. That means the temperature and the volume are going to change. And initially we have a gas with a volume of 22.4 liters and 27 degrees Celsius. Remember what I said? You cannot use Celsius temperatures in these gas law problems, so we have to first make sure we know what this temperature is in Kelvin. Remembering that Kelvin is equal to Celsius plus 273. So 27 plus 273 gives us a temperature of 300 K to start for this problem. So it says here, what would the temperature be if the volume was increased to 44.8 liters? So here we are increasing the volume by a factor of, that's right, by a factor of 2. Going from 22.4 liters up to 44.8 liters means there's an increase in the volume by a factor of 2. Well, this is Charles' law, which says that if there's an increase in volume, there will be an increase, the temperature will also increase by the same factor. So we know the temperature will increase by a factor of 2. Since it started at 300 Kelvin, our temperature will increase to 600 Kelvin. All right, I would like you to try scenario number 2 for this problem on your own. See if you can come up with a reasonable answer without using any kind of calculator. You should not need a calculator. And we will meet again to discuss the answers to these 2 problems, and then we will take all of this to the next level. All right, this has been objective number 4 from Unit 13. I'll see you in the classroom.